I nevertheless will say a few things for the benefit of the students. So Cumrun Vafa graduated from MIT and went to Princeton in the early 80s for PhD studies. There he worked under the guidance of Edward Witten, and he achieved something remarkable, that your PhD thesis goes straight into textbooks. As you know, the Vafa-Witten inequalities are one of the handles that we have, one of the few non-perturbative handles that we have as strong, rigorous results on the behavior of gauge theories at strong coupling. And after this very nice piece of work, he went to the Harvard Society of Fellows to work as a postdoc, and I believe that probably it was a case of a love story with Harvard, because I think that he never left Harvard ever since, if I'm not mistaken. And there, for more than 30 years, he has been one of the leaders of the development of string theory. His influence in the history of the field is enormous, as vindicated by many honors, like, for example, the Dirac Medal from the ICTP, the Fundamental Physics Prize 2 years ago. Rather than listing his many achievements, I will just mention one which is kind of, in a sense, closer to my own interest. He's the co-author, together with Andy Strominger in the mid-90s, of a truly historical work when they, for the first time, computed black hole entropy using a completely quantum mechanical framework. This work was of historical importance because it affected strongly both string theory and other areas of physics, and its influence is still felt today. More recently, he has also been involved in putting out some markers for the future development of the field, or the role of string theory in the realm of theoretical physics. They go under the name of Swampland versus landscape, weak gravity conjecture, and I believe that this is something that he will talk about in his talk today. So I stop here, and please let's welcome Cumrun Vafa.
Thank you for this very kind introduction. It's a great pleasure to be here. So I guess I will assume that I don't see half of you guys, because half of you are part of the conference who involves a lot of expertise in string theory. So I assume my audience is not familiar with string theory. So I apologize for the half of the audience who may be familiar with it. So I'm going to basically start from stage one. What is string theory and why we are interested in it, and what are some of the issues in it? It is, it's one of the, as we in string theory love to say, it's basically the consistent framework that it gives us to study quantum theory of gravity is what we really believe, why we believe in string theory. The achievement of trying to have a unified framework to describe Einstein's theory in a quantum context is why we believe in this. Now, this is very non-trivial accomplishment, because all the typical approaches are either heuristic or don't quite go to in detail, whereas in context of string theory is a precise, quantitative, and in many ways, in many contexts, perturbatively computable scheme to do calculations the way physicists are used to. So it really gives us a handle on a quantum theory of gravity. But it involves something strange. It involves replacing what we think about as point particles with extended objects, which is what could be viewed as strings, one-dimensional excitations, or even, as we have learned further in the context of string theory, higher dimensional objects, membranes or higher dimensional sheets, to describe the fundamental entities. It is crucial that the fundamental entities are no longer just point particles. This is a revolutionary viewpoint, and it is actually still not deeply understood why we needed this. Why didn't point particles suffice? But it seems to be the case. We need to go beyond the theory of particles to the theory of extended objects. And one of the elegant things in the context of string theory is that these extended objects have geometric properties. Points you cannot do much with, like points can join or not join, but if you have extended objects, they can have an interesting topology. For example, two strings. If they move in time, they can join, or if you go backwards, they can split. And so the geometry of the word sheet, the sheet that they generate, is a nice manifold, in general, a smooth manifold. It could be, like in this case, a pair of pants. So these kind of interactions, which kind of mix physics and mathematics, geometry and topology with physics, seems to be a key fact about why string theory is a nice thing. And we can kind of describe the usual things we are familiar with, like quarks in terms of these fundamental objects involving these strings, or strings that can end on other extended objects, like what we call membranes or D-branes or other kind of extended objects. So they can have interesting relations with each other. They could either be closed or they could be cut open on these kind of sheets that we call D-branes. So they have interesting interplays between the various kinds of objects. So the objects here are particles themselves can break on other quote-unquote particles, in this case on sheets. So there's an interesting interplay between them. And it resolves the inconsistency that we know between quantum theory and gravity. But there is a key that is part of this resolution, which is the existence or emergence of these extra dimensions. The extra dimensions of string theory is on the first sight of it a nuisance. When I first was studying string theory back in the 80s, this was a feature that when string theorists wanted to talk about, they would be very embarrassed to talk about it, because we live in three-dimensional space, and string theory doesn't quite work in three-dimensional space. So it required extra dimensions, and so when extra dimensions come into the game, they say, wait a second, our universe doesn't have extra dimensions, so what are you talking about? And so string theorists embarrassingly say, well, maybe they are too small to see. Sounds a little bit funny from a physicist viewpoint that everything is tailor-made to be applied to our universe, but has the wrong dimension. So it's a little embarrassing, you could think, that we need extra dimensions for the theory to be consistent. But on the other hand, it's an interesting thing because it predicts the dimension. This is not a typical thing in physics. In physics, you don't predict dimension, you start with a dimension. But in this theory, you cannot just start with any dimension you want. So that feature is good, except that you wonder, why does it give such a high dimension? On the negative side, it could have been it's smaller than 3 dimensions, then it would have been very bad, because then we had no hope of getting our universe. But luckily, it's at least bigger. So there's a 50% chance, if you wish, to have it on the right side, or maybe more. But at any rate, we ended up on the right side. It's bigger than 3 dimensions. So at least we can imagine these extra dimensions to be curled up or some interesting geometry associated with them. So we draw usually these sheets. We have the usual flat space, but we say that these dimensions are not on the same footing. What does that mean? Well, some directions could be curled up like a circle. So if you think about rolling the sheet to the cylinder, that's a way to think about it. Of course, from physics, physicists are thinking this picture might find this a little strange, but there's another way to think about it physically, which I think is more natural. In physics, we are very familiar and comfortable with the notion of symmetries and the spontaneous breaking of symmetries. So we should think about the extra dimensions as having, in general, having extra symmetries, where you can go from rotate one dimension into another. A situation like this is like spontaneous symmetry breaking, where we have spontaneously broken the rotation between one direction and the other direction. That could happen in physics very naturally. So in this context, we could say that having the extra dimensions be tiny is related to spontaneous symmetry breaking, in this case, in terms of the spatial geometry. It's not that bizarre. So therefore, we are comfortable with having symmetries hidden from us, like in the Higgs mechanism that we are familiar in particle physics. This could also happen with the geometry of space. So that's not that crazy. So we think about every point in space having extra geometries like these circles, or in fact, the geometry is much more complicated than necessarily circles. If it were just circles, we would get a relatively boring looking physics in our universe, it turns out. So what we really want is some complicated one, like these spheres, but even that's too simple. And in general, we want something really crazy. And so since I do not know how to draw these crazy stuff, I appeal to some things that other people have drawn in terms of complicated geometry. So however you can imagine higher dimensional geometry. So if you're dealing with, let's say, 9 spatial dimensions, we need 6 extra spatial dimensions compared to the 3 space we are familiar with. And so you imagine these to be, let's say, a 6-dimensional extra space, complicated geometry with lots of handles and holes and this and that, which is very hard to draw, because in 6 dimensions it's hard to draw. But luckily, thanks to our mathematical friends, there's a very concrete way of thinking about these. So we have a lot of handle on these spaces. So we can even draw good pictures, which has nothing to do with the real geometry, but at least looks like good pictures. Actually, there are ways to draw these pictures more intelligibly, which do reflect the geometry, but I think I will pass on that. So for this, just imagine a caricature of pictures like different kinds of shapes or sizes and properties and handles and holes and all that. So it's reflected by this kind of artistic view of it, let's say. How many of these do we have? Well, here I have drawn a few of them, but it turns out that it's almost uncountable. Well, we think they're countable, but essentially it's so big that you can view it as almost uncountable for practical purposes. It's a huge number of such possibilities. So, okay, so that's nice, or maybe bad, I don't know. It looks like a complicated story there. What's going on? Well, first of all, it's a good art gallery we can have of all these possibilities. That's one possibility. But what does it do to our universe? How do we discuss our universe in this context? Well, first of all, different kinds of universes will have different kinds of strings in them. For example, the string can wrap around the cycles different ways for one case versus the other one, so that depending on what kind of geometry they have, you can have different kinds of configuration of strings. So it gives you a totally different physics based on what kind of thing you pick. So the physical properties that we observe, like whether you have elementary particles like quarks or electrons or photon, how many of them do you have, how many kinds of light particles you have, what are their masses, what are the forces between them, all of these questions will depend on details of what you choose for these manifolds. So there's not a unique choice. Worse than that, for each one you have a huge number of possibilities depending on shapes and sizes that you pick. Very complicated possibilities. And this choice, this collection of choices is named the string landscape. Landscape in this context refers to the possibilities of what you pick as the internal tiny compact spaces that we need to have in order to connect the higher dimensional theory, 10 or 11, back to the 4-dimensional theory that we are trying to observe. Okay, string landscape, but the varieties is huge. But what we see in our space, for example, if you think about our space as this extended plane here I'm drawing with this blue curve, and the internal space to be, let's say, this red geometry here, in this case it's like a donut figure, like torus. Depending on what objects you have here, the objects which wrap around, like strings which wrap around the cycles on this geometry, they wrap around it at any particular point in space. So in other words, for every point there is its own donut or torus above it, and you can wrap a string around it, and that means effectively you're putting some energy at the point that you're wrapping it around. So from the viewpoint of this extended 3-dimensional space, they will look like a point particle. Even though they are not a point particle, they are strings in reality. But since this space is so tiny, you will not see it very clearly. As far as you can see, it looks just like a point in space. But of course, you can have different kinds of string configurations, depending on whether it goes this way or the other way. But from your perspective, in the lower dimension, they just look like different color particles. Color by color, I mean different kind of charges or masses, depending on which cycle they wrap around. So it's hard to distinguish them that clearly from the viewpoint of the lower dimensional theory, but from the viewpoint of the full theory, the dictionary is upstairs. It's like somebody has a dictionary, and that dictionary is the geometry of the internal space, and you open it up and it tells you what are the particles, what are their masses, what are the structures, how do they interact. All of them are hidden in a code, in a geometric code, in the internal geometry of string theory. So it geometrizes physics. So physics is now becoming a geometric language about how these things fit together, what are the interconnections between them, and it's hidden from us, which for us which live in this big space. So these tiny spaces is a way to encode physics in a funny way, in a mathematical way. Again, you can have different kinds of configuration giving rise to different kinds of particles. So, as I said, this leads to what we call the vast string landscape. Now, what this means is, well, a picture like this, but what I mean more specifically is that for each one of these choices of the internal geometry, we get a different kind of universe. Each one of them represents a would-be consistent universe. One of them is there, etc. So by this landscape, I mean every point of it is a would-be universe. This not the totality of it is not one universe, as we usually talk about landscape. But here what I mean is that every point on this landscape reflects a possible universe. So we have a huge number of possible universes, depending on which ones we take. People have tried to estimate how many such universes there are. As I said, it's almost uncountable in practical terms. People give numbers like 10 to 600, 700, 10 to the, I don't know what numbers. But anyhow, it is not, depending on what subspace of it you look at, you can try to count them. But it's basically, the main point is that it's effectively so big that you can think about this whole thing as populated. That every point you pick here, there will be something like that which corresponds to it. So then that got very interesting because even though our universe is just one of them, which we don't know where it is, etc., one of them is our universe, but we have this whole totality of would-be universes. But this is complicated because if you want to deal with these higher geometries, you have to build the space and do various studies of them, and it's not easy math. It's fun math, but not easy, and the variety is huge. And however, if you want to study what are the allowed universes, if that's all you're interested in, you might just say, okay, forget about where I got them from. Let's just study everything that we can possibly imagine could be part of this landscape. Just tell me how many electrons you want, what masses you want, how many quarks you want, what interactions should they have exactly with each other, and somebody, string theorist who doesn't have any better thing to do, will try to construct that geometry for you at some point, so you don't have to waste your time with that. Just study whatever physics you like. In other words, physics is something, as soon as you write, you want a particular property of spectrum of physical particles and their forces, you might as well start with there, and don't waste your time with constructing complicated mathematical objects. That was kind of becoming the attitude in string theory in the early 2000s, where people were beginning to say, look, you just write down your effective theory that you like, somebody will construct it for you, and we don't need to know too much details about the rest. So basically, if this is the case, it makes string theory essentially useless. Because the whole point of string theory was to predict our universe, and we now know our universe is only one of these huge set of possibilities. And if we cannot find our universe there, and if anything you can write down, if anything that you think is okay is effectively possible, and somebody out of these zillions of possible geometries can give you that, who cares which geometry? We can reverse the problem and say, I just study with the physics I like, and somebody will construct it, and therefore there is no predictive power. If this was the case, string theory will be completely unpredictable, unpredictive. There's nothing that can come out as a prediction of string theory. This would be bad news for the fundamental theory, because then we would have no predictive power, and that means it is not science. We need to have some predictions. So therefore, that is a conundrum for string theory. What is it? So this is what I was just saying. So this raises the question, can we just reverse this and pick a consistent looking 3+1 dimensional theory and not worry where it came from? But let's ask it more seriously. Can any imaginable universe occur as a point in the string landscape? Well, you could imagine some crazy things, like particles which would have had gauge charges have a funny interaction which is inconsistent because we know enough about what gauge forces mean. So what I mean is that, well, we will write what we think is consistent in the usual way, like we know how quantum field theories work, we know how particles get their charges and all that. So write something which you think is consistent. Is that good enough? Once you write something which looks consistent, can you come up with something which comes from some geometry? Can you geometrize anything that looks consistent? The answer turns out to be no. And that's the key point here, In fact, it turns out to be the opposite of what I was presenting. Most consistent looking theories you can think of in 3+1 dimensions are not consistent theories we think of quantum gravity. That is, we don't believe the most generic things you write down will arise in string theory. In other words, most of the things that I was drawing for you as part of the landscape is not possible, and they belong to what we call the swampland. They look okay, but if you go closer to it, there's a swampland. You cannot live there. It's not a livable universe. That universe, in other words, is inconsistent, even though it looks consistent. It's just fooling us. Quantum gravity is more subtle consistency conditions that we haven't quite figured out, but we believe most of these are not allowed. That would be, of course, a great news for string theory, because it tells you it is very predictive. It doesn't tell you exactly which one of the universes, which one of the landscapes of string theory we live in, but it does tell you that many of them that it looks okay, are not actually allowed, are not going to appear. That would be what you think a predictive theory should be. So if you think about this geometry, you have some points of landscape fine far away, but typically most of it is actually what you call a swampland. So the main question becomes, what distinguishes the string landscape from the swampland? What is the map which identifies the boundary of the swampland landscape? You know where not, or what is the thing? What is the dictionary? Well, we do not know what these consistency conditions are, which we actually need for a consistent quantum theory of gravity. We don't know that. What do we know? Well, all we know is studying these zillions of geometries and see what kind of physics we get and what kind of patterns of string landscape emerge. By definition, everything that we can get from a consistent geometry is an allowed physical universe. We could see what is the image of this map from the geometry to what we get, and what we are not getting as saying, well, those should belong to swampland. And try to understand, at least heuristically, what these criteria are and where are they emerging from. So if we do not know exactly these conditions, we can just do this. So we know already that not all constant theories arise from string theory, and this can be captured by some principles, and at least some of them can be motivated based on quantum gravity, and specifically about black holes. It turns out quantum gravity, where we know not much about actually, even though we have studied it for quite many years now, there are a few things we have learned about quantum gravity, and we have learned the central role that black holes play, quantum aspects of black hole play in the context of quantum gravity. And many of the properties that emerge as necessary requirements for string landscape has a heuristic explanation in terms of what we have learned about black holes. So I will try to say some things about these. Now, these can lead to some specific predictions which have concrete consequences for cosmology and even for particle phenomenology for our universe that I will try to mention. So the plan for the rest of my talk is to give you some of these criteria for the landscape that we have discovered and explain their motivation and some of their observable consequences. So let me list some of these possibilities, and then I will describe one by one what these are. In physics, when we talk about quantum field theory, for example, we have symmetries. And the symmetries can be what we call global or gauge symmetries. And what the difference between them is, in the context of gauge symmetry like electromagnetism, you have electrical field coming out. But you can have symmetries like you can count particle numbers, but there may not be any extra electrical field associated with this. So those we call global symmetries. If there's electrical field associated with it, we call it gauge symmetries. So it seems that even though both are possible in a theory without gravity, with gravity you only have gauge symmetries. there is no global symmetries allowed in the context of quantum gravity theory. Moreover, all the possible charges that you can think of, for example, electric charge 1, electric charge 2, etc., not only can appear, but should appear in a quantum theory of gravity. So all the possible charges should be realized by some state in your theory. Now, in quantum field theory, when you talk about a field, the field can take usually any value you want. For example, if it's a real number, it can take any value from minus infinity to plus infinity. It turns out that, morally speaking, this is not true in the context of quantum gravity, that if you restrict your attention to a given energy scale, once you fix your energy scale, for that energy scale, the range of the fields are always finite. So some kind of compactness in your field space, which is not typical in field theories, but seems to be there for quantum gravity. The theory must admit light higher dimensional objects. Now, this is kind of turning string theory on its head. Of course, string theory is extra dimensional object, but you can actually learn from some of these principles that why it had to be so. Why there had to be extended objects. Why point particles does not suffice. So these principles actually are strong enough to actually tell you that the theory must have extended object. So give us a conceptual explanation of why we need some extended objects for quantum theory of gravity. Gravity is always the weakest force. So I will describe aspects of this. We know in our universe gravity is the weakest force, but we have seen this is the case also in the context of string theory, that whenever we compute this particle spectrum, the force between elementary particles is always stronger than the gravitational force between them. Gravity always ends up being the weakest force. And the next question is the fate of our universe. How does the current universe look like? We talk about the notion of having a dark energy that permeates the whole universe, and in this context of gravitational physics, Einstein's theory would suggest that that may be related to a space called de Sitter space. What are the fate of de Sitter space, and what is the fate of our universe in the context of string theory? So these are some of the things I would like to discuss. So let me first remind you or explain to you some of the basic facts about black holes, which will be relevant for us. Fix a particular charge. It could be huge charge and a mass. Big mass and a big charge. Astrophysical masses, huge like solar masses and huge charges. It turns out that as long as the mass measured in Planck units is bigger than the charge, you can construct a solution to Einstein's equation, which have nice properties. It gives you basically all the masses accumulated in some small region with electric field emanating depending on what the charge Q is. This gives you the black hole. In these contexts, you find that there's a sphere surrounding the object called the event horizon, where if you get closer to it than that, you cannot escape. So this is the story about black holes. And the extreme case, when the mass equals to charge, is also limiting case of this, which is called the extreme of black holes. It can also be realized as a limit of this case. So as I just mentioned, all black holes have event horizon, and anything crosses it cannot get out. Now, this is the second point, is the most important property for quantum aspects of black holes, that the black holes have thermodynamic properties. This was discovered in the early 70s, 1970s by Bekenstein and Hawking. And in particular, the black holes carry an entropy, which is given by 1/4 of the area of the horizon of the black hole. So that's a fact that was discovered by Bekenstein and Hawking using semi-classical quantum gravity arguments. And this has been realized in string theory in the way that is rather satisfying. For the case of Einstein's theory, if you solve Einstein's equation, there's a unique solution. So the entropy is 0. There's no possibility. On the other hand, thermodynamically, you predict, sorry, but quantum mechanically, you predict that there must be much, much more. The area of the horizon of an astrophysical black hole is huge, so in Planck units, if you measure them, gives you a huge entropy. Namely, the number of configurations is exponential of area over 4 in Planck units, which means a huge amount of degrees of freedom. Where are they? Well, this is the first case where we become less embarrassed about the external dimensions of string theory. It turns out that those degrees of freedom of black hole, in many of these examples we understand in string theory, correspond to these strings or membranes or other things which are wrapping around the cycles of the extra dimensions. So the extra dimensions are where these entropies are hidden, where the degrees of freedom are hidden. So that becomes a useful fact suddenly from the viewpoint of a three-dimensional physics, which is where is it? Where is the microscopic state? And then it's there. It's that inside those small spaces is hard to see. So that's a good application for them. So, so this is what I was just telling you. There is this black hole of given mass, given charge. There's a horizon. And the entropy of it, the number of states is exponential of the area over 4 as the number of degrees of freedom. Now, all black holes disappear by gradually emitting elementary particles. So you have this fat black hole with charge, and gradually they kind of radiate. This is what's called the Hawking radiation. They gradually get rid of the masses and the charge, gradually until they completely disappear, and nothing is left. And there's no imprint left, we believe, of the black hole. The black hole gradually just melts away. Slowly, as it gets closer to the end, it gets faster, but the beginning also is a very slow process. It gradually emits particles. Okay, so these were just the facts that I want to use about black holes to shed some light about some of these statements. So the first criteria I mentioned was that the only symmetries we have are gate symmetries. That is, when you count something, this counting has to be associated with an electric force, electric charge. You cannot have a counting of an object which is a symmetry without having electrical field emanating from it. In other words, there are no global symmetries, we call. Suppose to the contrary there were global symmetries, you can count. Like suppose you had electrons which had no electric force. You could say electron number 1, electron number 2, you have 5 electrons, 10 electrons, you can count them. And suppose the electron number is conserved, it doesn't disappear. But suppose there's no electric force. What is going to happen? Well, since the charge is global and there's no residual electric force emanating from it, you can imagine having a black hole and throwing these electrons inside the black hole. Since we're assuming the electrons have no electric field coming out, from the outside of the black hole, all you see is the mass, and there's no sign for the charge because the electric field doesn't come out. As the black hole is evaporating, there is no particular number, there's no preference towards emitting electrons because there's no information that there's an electron inside. So when the evaporation of the black hole happens, it happens symmetrically between either any charges of those electrons by the process of the evaporation. And therefore, you can throw in electrons, and at the end, the net number of the electrons that you get out is 0 because the black hole has evaporated to nothing. And so you get a violation of the electron number. That means a black hole is a machine which crunches and gets rid of electron charge. So the global charges are violated. So in other words, if you have a charge Q, which is in this case you can view it as like counting the electrons, falls inside the black hole, you don't see any trace of it whatsoever, and the evaporation of the black hole is completely ambivalent to what went in. It's as if it didn't fall in. And since the process of with or without the electron falling is the same, at the end of it, you'll find in one case or the other, you will not have the same conservation that you're looking for. So you violate the global charge. It's a very simple idea. It disappears. With it disappears the electron number. You violate the global charge. So that's a simple argument which suggests that all the symmetries that we have in physics should be related to some kind of electric force. This is seen in all the examples we have in string theory. And we believe it's a part of our universe as well. The second criteria is that all the possible, if you have one of these electric forces, electric charges, all the possible charges should appear in your theory. For example, you cannot have a situation like if you have electron, there's no electron with charge 1, but there's an electron with charge 5 is the smallest number that you get, and nothing with 1, 2, 3, or 4. All the charges should appear in your theory. Now, why is that? Well, in the context of, if you just studied quantum theory of electrons, you could imagine easily a situation where electron only has units of 5 charge and nothing else in the theory, so everything appears with multiple of 5, but 1, 2, and 3, and 4 don't appear. It sounds perfectly conceivable, but in the quantum theory of gravity, in the context of string theory, we don't see that. We always see all the particles which are allowed, all the spectrum is realized in the theory. So why is that? Well, the reason, again, is easy to explain using black holes. You take a black hole with a given charge. You write a solution to Einstein's equation with any charge which is allowed in the theory, you can write a solution. Therefore, you have a black hole at least. And then Hawking and Bekenstein tell you, based on their count of microscopic degrees of freedom, or studying basically more precisely semi-classical aspects of black hole, that should carry entropy. And therefore, what does that mean? That means for that particular charged black hole, for that charge Q, there is not only one state, there's a huge number of states in the spectrum of the theory with that charge. There's exponential of A over 4 of them, and therefore, since A is huge, you cannot say there's none. So for every charge, there should be some state. Okay, so this is a kind of an explanation about why we expect all the charges to be occupied or allowed or appearing in the context of quantum gravity. So let's talk about the next criteria, and that is that the range of the fields is finite. So consider a field. Field is just some object which takes values in the whole space. In this case, I'm denoting it by this variable phi. And typically, in quantum systems and quantum field theories, we usually take this range to be over all real numbers. So it can be any number from -infinity to +infinity. However, it turns out in the context of quantum gravity, it seems like the range of this field cannot be infinite. And it seems like this range is bounded by the Planck scale, the mass of the Planck. So this range is bounded. It cannot be infinite. So this is one of the properties that seems to arise in the quantum gravity context. And we do not have a deep explanation of this fact, but it is observed in all the examples of string compactification that this is the case. In fact, in this conference, we just heard a talk about this, more technical than my talk clearly, but it basically talks about that if you did consider the range of delta phi much bigger than in Planck, you find that you get, if you try to do that, you can in principle conceive of bigger ranges than Planck, but when you do that, you find a huge number of light states, a tower of light states, emerging exponentially small in mass as delta phi becomes bigger and bigger. So that means that you will get automatically an infinite tower of states if you go beyond this range. In other words, if you want to restrict your attention to your theory with a given cutoff that you don't want to have light states, then you better restrict the range of your field space. So the field space is effectively compact. This innocuous statement, or not so innocuous, depending on your viewpoint, I will now argue, will imply that quantum theory of gravity must involve extended objects. This statement is equivalent to saying we need point particles won't work. So why is that? I now show you that this is just that, it's that simple. This statement is equivalent to saying string or something else beyond point particle is needed. And the reason is the following. So first of all, what does this picture mean? It means that if you look at the range of your field space, if you start with any given point, if you go farther and farther from a given point, infinite distance away, you get regions where there are light particles light particles, when the tower of light particles come, this description of an effective Lagrangian breaks down. So your Lagrangian description, your effective physics description only is in a small region in space. And if you want to go farther away in your field space, you'll get new description. And these new descriptions, where these light things appear, which we have learned is a crucial piece of what we call in string theory dualities. That existence of these would-be corners give you different perspectives about the theory in terms of the vantage point of these new light states. Each of these new light states suggests a new perspective of a Lagrangian, which looks very different from any other corner. And the existence of such a picture is exactly what we mean by the appearance of duality symmetries of string theory. So, but before I go on to what this implies about the extended object, one thing it implies is that the inflation, the way we think about inflation, cannot be as simple as people usually envision in field theory. In field theory, people just write down a field space phi, and they take it to be a long range. In fact, they want to have a flat potential which goes like large magnitude in Planck scale, or a much larger range than just one Planck unit. And they assume that their field Lagrangian is perfectly fine. No light states are added to the Lagrangian, and they just describe it with the Lagrangian of that one scalar field. That kind of context, slow roll inflation, that's one of the models for the popular models for inflation, just does not seem natural in string theory and seems like problematic. So this suggests that our notion of what inflation is, if it's true, has to be changed. It's not the usual picture. So these kind of radical statements coming from string theory will have impact on early universe and how we view the early universe. We cannot imagine a good old Lagrangian. If you just write down a good old Lagrangian, as people did in inflation 30 more years ago, it doesn't mean it's possible to realize them in string theory. What you can imagine is a conceivably perfectly okay field theory does not mean it's allowed in quantum gravity. And that's the lesson of the string Swampland. So the naive form of the inflation belongs to the Swampland. It is not allowed in string theory. Now I will explain why the previous criteria will tell you that string theory, or the theory that we're more precisely the quantum theory of gravity, must involve extended objects. It cannot have just point particles. For example, in M theory, the natural object is a membrane. In string theory, the natural object is string theory. It's always some extra object in the game. You cannot just have point particles. So I will explain how this heuristically at least follows from the previous criteria. Consider compactifying the theory in whatever dimension you're starting with on a circle. If you put the theory on a circle, from the viewpoint of one lower dimensional theory, when you take the circle to be a small size, the radius of a circle is another field, because you can adjust it at any point in your space. So you get an effective theory, which is a Lagrangian in one lower dimension, which in it will have a field like gradient of some field squared, where exponential of that field corresponds to the radius. Okay, so what? There's no problem with that. You just have a radius, which is a field which is controlling the overall dilation of the circle. Now consider the radius much bigger than 1. If you take the radius much bigger than 1, the theory from the vantage point of the lower dimensional theory will have a lot of light states. What are these light states? These are just the usual momentum states of a particles. If you have a gravity, for example, you have particles which are momentum states around the circle. The energy, as usual in quantum mechanics, goes like n over r. So therefore, as r becomes bigger and bigger, they become lighter and lighter. And since r is exponential in phi, you get this tower of light state as phi gets infinitely big. This is an example of what I was saying, that if you take the field range to be large, you get a tower of states coming down. In this case, the tower of momentum states, what we call in this theory the Kaluza-Klein tower, the tower of all these light momentum states, emerge. However, you can go the other way. You can take phi to be much less than 0. The radius, instead of growing, you can imagine radius shrinking and shrinking. If you did that, in a point particle theory, all these momentum states that I talked about becomes very massive. They go like n over r, and r goes to 0. It becomes infinitely massive. So they are not light at all. Therefore, you can take this phi to minus infinity all the way without encountering any tower of light states. But this is in contradiction with the assumption that every field range should be finite, and if you go too far in any direction, you should hit some light state. This cannot be the case. What does that mean? If you take the radius of a circle and take it smaller and smaller, the theory must have some light state. If the theory is only about particles, that can never happen. So for this to happen, you have to have an extended object which feels the overall size of the space. It could be a string or a membrane or something. It has to be able to feel the extra size. So when it wraps around that extra size and that size shrinks, the energy of it goes down because tension times the wrapping of the space gives you the effective mass or the tension of the lower dimensional object. So from this viewpoint, the emergence of string itself or membranes as fundamental entities will be predicted just by assuming that infinite distances is not allowed. So that is a more fundamental principle, perhaps, than string theory itself. That the idea that you cannot go too far in field space without encountering a tower of light states is a more predominant principle than string theory or M theory, because that in particular predicts the existence of extended objects. So this is the only natural mechanism we have as r goes to 0 is to have extended objects. So this is in some sense predicting the string theory, quantum gravity needs extended objects, string theory or whatnot. Next criteria is gravity as the weakest force. So it has been observed in string theory when we consider charged objects. When we look at the electric force between charged objects, the electrical force is the repulsion between two same electrically charged objects, this red line, is always bigger than the gravitational attraction given by this blue attractive force. In other words, the mass of the elementary objects is less than or perhaps equal to the charge. They both go like 1 over r squared, but one of them is bigger in magnitude than the other. So gravity is the weakest force. And this is, of course, true for our universe. The electron's repulsion is much stronger than its gravitational attraction. We typically ignore it. And when we talk about, for example, atomic physics, the gravity is so weak it's irrelevant for discussion. It's only for neutral objects that gravity has any role to play. So what is the black hole explanation of the weak gravity conjecture, that the gravity is the weakest force? Well, suppose we start with an extremal case where the charge of a black hole is equal to its mass. This is an extremal case, and effectively we believe all such objects, except so for some very exceptional situation, which I will come later, we believe these will decay. So for it to decay, you must emit elementary light objects out of this. So it undergoes Hawking radiation. So you emit a tiny particle, let's say, of charge q and mass m, and the charge of this guy goes down to q minus q, and its mass goes down to m minus m. This is still a black hole because it was fat object. It's still fat even after it spits out a little particle here and there. So after it emits this particle, it better be that the mass is still bigger than or equal to its charge. So m minus this tiny mass that it emits out should be bigger than q minus this tiny q. This is just the charge conservation and mass conservation, which implies, just by looking at it, that m should be bigger than q. So the small elementary particle has a bigger mass than its charge. So it's opposite to what black hole is doing. So the black hole has mass bigger than the charge, but the elementary particle is actually the opposite. That the elementary particle wants to go mass bigger than charge. This gives you at least a heuristic argument. It's not a proof, of course, but it gives you a heuristic picture of why this may be true. Again, in the context of black hole physics. The mass equal to charge actually does occur in string theory only for supersymmetric theories. Yes? Sorry? Yeah, the reversing. I have to look at what I did here. Okay, I have to look at my my algebra. But anyhow, it follows from the emission process of this and the fact that there's no elementary particle at the end. So there are further evidence for the weak gravity conjecture, which is based on Maxwell theory coupled to gravity. And it's related, this is probably a stronger evidence, which I would say is what I would find very unexpected evidence for it, that gravity has been found in the context of coupling to Maxwell theory, giving you trouble. And the trouble it gives you is the following. For a sufficiently strong electrical field, if you consider no electrically charged object, it turns out the gravity violates the gravity force, the electric force violates what is called the cosmic censorship, which is the following, that typically we believe that if you have a singularity in the Einstein's theory, there's a horizon surrounding it. Now, people have constructed solution coupling Einstein's theory with electromagnetism, and they have found that if you have a strong electrical field, you can find naked singularity violating cosmic censorship. Well, this weak gravity conjecture resolves that problem in the following way. It actually gives you the following statement. First of all, quantum gravity with electrical force tells you there must be electric charge. That's the statement that all the charge states are occupied. That's number one. Secondly, when the charges are occupied, it must mean that the charged occupied states have a property that the mass of them, the mass that they have, is smaller than their charge. Gravity is the weakest force. Therefore, if the mass is less than the charge, then it implies that if you take a strong electric field, their mass is less than the charge, it can easily create these electrically charged objects because the mass is tiny or smaller than the charge. And what happens is that when it creates these particles, these charged particles screen the electrical field, it gets rid of the naked singularity that it was otherwise there. So it turns out that precisely when the mass equals to the charge, that limit, it exactly reverses the order and it avoids the cosmic censorship problem. So this is actually an interesting resolution of connecting the weak gravity conjecture with that one. So, so this is the statement that I wanted to say. Let me just see what over here. But yeah, this was. So I just wanted to say this should be the other way, of course. That's, you realized, right? I meant to say mass is smaller than the charge, not bigger than the charge. I just had a typo here. Is that clear? So, so anyhow, but I think this particular one is a far more striking evidence that this is far more striking because it actually shows you a fact about general relativity, something Einstein would study, had nothing to do with quantum theory per se, knows about the weak gravity conjecture in this way. If you assume that singularities are closed, that there is a horizon around them. So this is actually quite remarkable that it connects two facts that you don't think necessarily are any relation between them. So it gives us further reason to believe in it. You can extend the weak gravity conjecture from particles to membranes. So if you have particles, instead of replace them by sheets, they have a repulsion force between same sheets, just like electric charge of the same charge, they have repulsion, and there's an attractive force. And it turns out the attractive force, again, is weaker than the gravitational, than the electric repulsion. This suggests that, except in the supersymmetry case, where the mass can equal exactly the charge, this is what we call the BPS condition, these would have typically led to, we would get in the context of these, what we call the non-supersymmetric situation, an ADS, anti-de Sitter space, but the fact that if you have same sign object, the repulsion force is stronger than gravity, if you put these sheets next to each other, they'll fly apart. The gravity force will not be able to keep them together. The electric repulsion wins. You don't have a stable anti-de Sitter made up of these same charged sheets. So no non-supersymmetric ADS is stable. Okay. Now it turns out that if we consider compactification of our universe in 3+1 dimension on an extra circle, we can end up with a known particle spectrum, yet an anti-de Sitter space, which is not supersymmetric because our universe is not supersymmetric, solution. And this was already observed a while back, except it depends on precisely what are the masses of the elementary particles. We know the masses of the elementary particles in our universe, so we can compute them. But the masses of some of the particles we don't exactly know, and their types. So these are in particular include the neutrinos, these light particles. We know they have some masses, but we don't know exactly what their masses are, and we don't know exactly what type of masses they have. So depending on what these masses or types are, we may or may not have these solutions when you go down in circle. If we believe that the fundamental theory does not allow it to have stable ADS solution, and if we found stable solutions using these compact deviation, then we would say that, the range of masses which allows you this to happen must not be possible. Therefore, we will make a prediction about particles. We can make a prediction that the spectrum of the neutrinos or the masses or such and such. And this actually has been one of the interesting predictions. In particular here by Ibanez and company, this has been studied, and it has led to an interesting statement about the masses of the neutrinos. And in particular, it also leads to some new version of understanding how the weak scale, which is the same scale as the Higgs particle is found, is related to the neutrino scale and the grand unification scale. So it had been observed that by a certain mechanism that the Higgs scale, the scale of the mass of the Higgs, is a geometric mean between a grand unification scale where all the forces unify to one force and the neutrino masses. And this actually, given the bound that one finds on the mass of the neutrinos from this lack of ADS solution, it makes a prediction of the scale of the weak scale, which is an amusing way of reformulating what hierarchy might mean. Why is the weak scale so small compared to the dot scale? So let me go on to the final criteria for what I want to describe, which is the fate of our universe. Now, we know the universe had a beginning. After all, we exist. Does it have an end? Well, a particular Swampland conjecture suggests that indeed there is an end to the universe. And this is the following picture. So first of all, this is the usual picture you may see about, early universe involves something, maybe inflation, maybe something else, some quantum fluctuations, and how the CMB has taught us about the anisotropies in CMB has led to this structure formation of galaxies and so on, and universe as it expands cools off and gives you the structure that we observe here. And now the dark energy seems to be dominating and giving rise to further acceleration of the universe. Of the order of about 14 billion years is the scale of the universe in terms of temporal history from the beginning till now. Okay, that's our time. Will it end? Well, the only universes that last forever in string theory have a property that we call supersymmetry, which I have alluded to. Now, all the universes which could have conceivably lasted forever seem to belong to the Swampland if they don't enjoy this property. So in other words, supersymmetry, which tells you that for every integer spin, there's a half-integer spin object exactly of the same mass and same properties. They're one-to-one correspondence between what we call bosons and fermions. It's found that the half that corresponds to the particles that we have observed do not have any counterpart. So the bosons don't have fermions, and the fermions don't have the bosons, so there's no pairing between them, and therefore supersymmetry is violated or spontaneously broken, whichever it might be, in our universe. So we do not have supersymmetry in our universe, and therefore, according to what we know best, is our universe will not last forever. So we don't believe our universe is stable. Okay, good to know. How long do we have? Oh, we have passed our time, right? But we have a few more seconds perhaps. So let me continue. So, so this is the age of the universe I'm drawing here in log scale. 10 to the 0, 10 to the 10. These are in years. This is roughly where we are, about 14 billion years, 10 to the 10 years. Protons decay around 10 to the 35 years, perhaps. That's what we think. Well, that's a long way from now, so we don't have to worry about that. Many more years to come. We're here. actually our universe seems to have dark energy. That has been measured. And the dark energy leads to a natural time scale.